Hello again, and welcome back to C++ real-time audio programming with Bela. We've been going through the basics of synths and audio effects, covering them in the C++ programming language. In today's lecture, we're going to be looking at a generic and widely applicable programming concept known as the state machine. The state machine is useful for all sorts of different applications, both hardware and software, and in today's lecture we're going to look at a number of different examples, starting with an update to the metronome example we built in Lecture 9, and ultimately working ahead toward the ADSR, or Attack Decay Sustained Release envelope. We won't cover that one until the next lecture, but the state machine is an important foundation for being able to build it. Over the course of this lecture, we'll define what we mean by state machine, and we'll talk about how they're structured and implemented. We'll build a metronome which keeps track of which beat in the bar it's on, marking the beginning of the bar line with a higher pitch tick. We'll also see how state machines can be used to clean up noisy sensor data, including debouncing push buttons and implementing comparators with hysteresis. Hysteresis is essentially a state-dependent variable threshold, which we can use to make our comparators more robust to noise on our signals. As always, you can find the companion materials on GitHub with the link at the bottom of the screen. Also, as always, these examples run on the Bela Starter Kit or the Bela Mini Starter Kit. Today's examples will also use some external hardware, most importantly a push button mounted on a breadboard. You'll need a resistor for the push button, and you'll also need an LED. One part of the lecture will optionally use a force sensing resistor, although you can substitute a potentiometer for that particular example. Okay, let's dive right in. This is a lecture about finite state machines, or just state machine for short. A state machine is a simple mathematical model of computation, which turns out to be useful for a wide range of practical applications. Let's define the state machine according to its four basic requirements. First of all, a state machine needs a finite set of states that the system can be in at any given time. We're going to build up an example as we go along here. Our example state machine is going to have three different states that it could be in. Any state machine must be in exactly one and only one of these states at any given time. A state machine also needs a set of transitions to move between the states. In this example, we can see that certain of the states can transition to other states, but not uniformly so. For example, state 1 can go to state 2 can go back to state 1 or to state 3, but state 1 can't go directly to state 3. A state machine will also take a set of inputs, which determines which transitions are operative at any given time. In this particular example, state 1 moves to state 2 when a button click occurs. If we're in state 2, a button click will move us to state 3, or if we're in state 3, a button click will move us back to state 1. Alternatively, in this example, if we were in state 2, a timeout could occur and bring us back to state 1. The particular kinds of inputs that are involved will depend on the application, but they might include sensor inputs, timing events, or other forms of external communications. Finally, most state machines will also generate a set of outputs. The outputs might depend on which state we're in at any given time. In this particular simple example, we have an LED and we have a sound generator. In state 1, they're both off. In state 2, the LED is on, but the sound is off. And in state 3, both the LED and the sound are on. I want to emphasize that a state machine involves a finite number of states with deterministic behavior. What this means is that the transitions from one state to another must always be deterministic based on the inputs. This can include what we call self-transitions, where the state remains the same for multiple cycles based on the particular inputs. But again, at any given time, it should never be ambiguous what state we're in or what state we are moving to based on the inputs we've received. Alright, let's look at a slightly different simple example. Suppose that we had a system that blinked an LED, and we could push a button to start the LED blinking, and we'd push the button again to stop it from blinking. In this case, we could model the system as a two-state state machine. State 1 has the LED off, and state 2 has the LED blinking. Those are its outputs. There are certain transitions between the states which are possible. They're shown in purple here, and the input that takes us between the states is the button press. So if the button is not pressed, we have a self-transition and the state remains the same. Notice that at any given time, the system is either in state 1 or in state 2, but not both. Sometimes, when we write these diagrams, we'll omit the self-transitions just for clarity. The implication is if no other transition takes place, then a self-transition has occurred and the state remains the same. Now we can also write the same state machine in a different way, where instead of having two states, we have three states. Here we have state 1, the same as before, but the blinking LED is implemented not as one state, but as two. State 2 has the LED on, state 3 has the LED off, and we toggle back and forth between these two states after every n milliseconds. The button press, as before, will take us from state 1 to state 2, and if we're in either state 2 or state 3, the button press will take us back to state 1. But while the LED is blinking, we're not staying in one state, we're oscillating back and forth between state 2 and state 3. I want to highlight a couple points about this example. First of all, notice that the inputs to a state machine could include the elapsed amount of time, and this could be used to generate a transition. Secondly, notice that the output of the state machine, in this case the status of the LED, is not enough information to tell us which state the machine is in at any given time. In version 2 of this state machine, if the LED is on, we can clearly infer that we must be in state 2 because it's the only state that has the LED on. On the other hand, if a brief observation shows us that the LED is off, we don't actually know whether we're in state 1 or state 3. The only way we could find out would be to wait for n milliseconds to elapse to find out if the LED subsequently came on. This is a particularly important point because very often we will want to generate state machines that have multiple different states with the same observable behavior, and the reason that we do it is that in different states they might react to inputs in different ways. We'll come back to this a little bit later. There are different types of state machines we might encounter. The simplest type of state machine is called a state acceptor or a classifier. This is a subclass of state machine that takes inputs but does not produce any outputs. A state acceptor is a way of recognizing a particular sequence of inputs by reaching a particular state when a valid sequence is received. A good example of a state acceptor would be a combination lock. The states might indicate which element of the code we're waiting to come in, and the inputs would be which numbers we put into the lock. In this particular example, we have a lock which expects a 3-digit code, 37, 8, 22, in that order. So the state acceptor would start in state 1, looking for the number 37. If it receives it, it moves to state 2, looking for the number 8. If it receives the number 8, it moves to the third state, looking for the number 22. And finally, if it receives the number 22, it moves to the final state, which is the accept state, where the lock opens. If it receives any other number at any other point, including these same numbers in a different order, it's going to move to the reject state, and the lock will not open. The more common type of state machine that we'll encounter in real-time audio is what we call a finite state transducer. We'll oftentimes just use the term state machine as shorthand for this. This type of state machine has both an input and an output that it generates. You can find all sorts of household examples of finite state transducers. One of them would be a common electric garage door opener. In this case, we have 4 different states. We have a state where the door is open, where the door is actively closing, where the door is closed, and where the door is actively opening. Basic mechanical constraints mean that only certain transitions between states are possible. For example, we can go from the open to closing state, from closing to closed to opening, and then opening back to open, but there would be no way to jump immediately from the open state to the closed state. A typical garage door opener takes a couple different inputs. The obvious one is the button that we click to open or close the door. Notice that the button click does a different thing depending on which state we started in. If we started in the open state, then clicking the button starts to close the door. But if the door was closed, then clicking the button starts to open the door. The other input that every garage door opener will have is some kind of sensor to tell us when the door is fully shut or fully open. So in the closing state, we'll wait for the door to become fully shut and then we'll move to the closed state. Likewise, in the opening state, we wait for the door to fully open before moving into the opening state. Finally, the output from this particular example is a control to the motor that opens or closes the door. The motor could have 3 settings. It could be off, it could be raising the door, or it could be lowering the door. So in the closing state, we would be lowering the door, waiting for the sensor input to tell us that the door was fully shut. At that point, we move into the closed state and the motor turns off. In the opening state, on the other hand, the door is going up, and we're waiting for the sensor to tell us that the door has fully opened to go back to the open state. You can see again here that just by observing the status of the motor, we don't necessarily know which of the states we're in, but it's very useful to have the open and closed states be accounted for separately because we want the button click to do something different in each case. State machines can become quite a detailed topic used in theoretical computer science, and there are a number of different mathematical models that we might encounter. In this particular lecture series, I'm mainly interested with the pragmatics of how to implement a usable state machine in our audio code. One issue of particular practical importance is when we generate the outputs of a state machine. We might consider generating outputs as singular events that take place whenever we enter a particular state. These are known as entry actions. We might also generate a discrete event whenever we leave a particular state, known as exit actions, or potentially when we move from one state to another state. We could also generate events continuously as long as we remain in a particular state. Formally speaking, we could think of that as an event taking place on a self-transition. But at a basic level, I want to highlight the difference between events that take place once only on moving between states and events that take place continuously as long as we are in a state. That distinction will be particularly useful for audio programming. From a mathematical perspective, it's useful to know a couple different terms that you may see around state machines. We can talk about the Moore model of a state machine, in which the output depends only on the current state and not on the inputs or any other extrinsic factors. We could contrast that with the Mealy model of a state machine, where the output depends on the current state and the inputs at the current moment. Ultimately, any state machine could be written in either model, the main difference being how many states we have to implement. But again, my practical advice for audio programmers is not to get hung up in the details of one particular model or another, but just to choose an implementation that is clear and simple and involves the minimum duplication of code. We'll look at some practical examples momentarily. Finally, I've said this before, but I'll say it again, it's very important to know that these state machines are deterministic systems. What this means is that our state machine should always have exactly one transition that is possible from any given state based on the current set of inputs. We need to clearly specify what the transition criteria are in terms of all the relevant inputs. Let's try to make this more practical in terms of audio programming. Let's return to the example from the previous lecture where we implemented a series of increasing and decreasing line segments. If we're going to implement this example as a state machine, how many states do we need? We need two states in this case, one for the increasing segment and one for the decreasing segment. Okay, what determines the transitions from one state to the next? The transitions are determined by the amount of elapsed time, or equivalently, by the line segment reaching its desired level. Now, are there any other inputs that we need for this particular example? In this case, no. The line segments are going to go up and down on a regular interval, and there are no other controls that we're using. Finally, what are the outputs of this state machine? The outputs are the linear envelopes, a rising envelope in the case of state 1 and a falling envelope in the case of state 2. So that's the basic idea for how we'd implement this example as a state machine. How would we do this in code? Practically speaking, we need a few things. First of all, we're going to need one or more variables to keep track of which state we're in. If our state machine is primarily implemented in a function like render, which is called all the time, then we may need a global variable to remember the state from one call to render to the next. The usual approach here is to use one single variable which holds all possible states of the state machine. We can assign one value to this variable at any given time to tell us which state we're in. In other cases, it might be conceptually clearer to use multiple different variables. For example, for the blinking LED that we turn on and off, maybe we want to use one Boolean variable to say whether the LED is blinking or not, and another Boolean to tell us whether the blinking is on or off at this given moment. The second thing we need to code up a state machine is a set of if statements. The if statements will check which state we're in at this given moment, and generate outputs and look for state transitions accordingly. Here's an example of that. Inside our render function, we might say if gstate is equal to 0, then we'll do a certain set of things, else if gstate is equal to 1, then do a certain other set of things. The else if is very important here. If we just did if state is equal to 0, and then later if state is equal to 1, then if we change the state inside the first if statement, then we might end up having both of our if statements run in the same block of code, and that may not be what we want. In most cases, your state machine code will be much more readable if you can give your states names rather than numbers. The name should describe what the state does. Therefore, I strongly recommend that in most cases you define a set of constants at the top of your file which associate names with numbers. This doesn't actually change the behavior of your code, it just makes your code more readable by not having to have magic numbers inside of your render function. A very convenient way of defining a number of constants all at once is with the C++ enum keyword. Enum stands for enumerate, and it's a way of defining a number of constants all at the same time. Unless you otherwise specify, the constants each get unique values in increasing order. The important part of using the enum is that after you give your states names rather than numbers, you should only use the names in your code and not the numbers directly. That means that later on, if you change the number of states or you reorder them inside the enum, it doesn't matter because you're only using the name inside of your code. Here's an example of this. We have the enum statement that's at the top of our file. Notice that we do need a semicolon at the end of enum, unlike declaring a function. We have our global variable gstate, which is starting in the state kStateOpen. We're using the k prefix here to indicate constants, in contrast to the g prefix indicating global variables. This is just a stylistic convention. You can choose your own, but whatever you use, I suggest using it consistently. Finally then, we have our function in which we're checking which state we're in and taking appropriate actions. That brings us to the next piece of implementation. Once we've used if statements to decide which of the states we're in, we need a further set of if statements to look at the inputs that we've received. The inputs will tell us what transition we need to take for the next time around. Remember that we don't necessarily always have to move from one state to another. We can always have a self-transition where we remain in the same state, and this may even be the most frequent occurrence. So notice that in this particular example we have nested if statements. The outer set of if statements is checking which state we're in right now. Once we go inside one of those if statements, we have a further if statement which is checking our input. So for example, if we're in the open state for our garage door opener, the motor will be off, and we'll have a further if statement inside of that to see whether the button push occurred. If the button push occurred, then we set the state to something else. Now this highlights an important point, which is that it's very easy to change state. All we have to do is assign a new value to the state variable. Once we do that, then automatically the next time this block of code runs, something different will happen because we'll be in a different state. Then finally, implementing a good state machine involves some planning on when it is that we're checking for transitions and when it is that we are generating our outputs. If we were implementing a state machine in hardware, and the edge of the clock would be the time that we evaluate our state and whether we need to make a transition. In the context of real-time audio, we can essentially use the audio frame clock for this purpose. In other words, each time through our for loop inside of render, which is counting the number of audio frames, we're going to check which state we're in and perform any particular actions and decide which transitions we need to make. As we discussed earlier, we also need to decide when to generate our outputs. Which outputs are generated all the time, as long as we're in a particular state, versus which outputs are generated only once we enter or leave a state. These might be different things. So let's pull all that together for the garage door opener. At the top of the file, at a global level, we have an enum statement which defines 4 constants. This means that we're never going to use the numbers 0, 1, 2, or 3 directly when referring to the state. We have our global variable called gstate, which we're starting in the open state. And then inside of our real-time looping function, for example the render function on Bela, we have our set of nested if statements. We're checking which state we're in, we're checking the inputs to decide if we need to move to a different state, and we are generating any outputs that we need for that particular state. Alright then, here is the first task of this lecture. In the companion materials, you'll find an example called Metronome Envelope. Back in Lecture 9, we built a simple metronome which played back an audio file on each tick. Metronome Envelope also counts timing, like that example did, but instead of playing back an audio file, it generates the click algorithmically using a sine oscillator and an exponential envelope. Your task in this particular example is to make a metronome that counts the bar lines. Specifically, you should make every 4th tick have twice the frequency of the other ticks. Therefore, you're going to need some kind of state variable which keeps track of which beat in the bar we're on at this given moment. In this case, where the beats have clear numerical meaning, you might not need an enum statement to name each of the states, and you might just be able to use the numbers instead. But the point is, in either case, whenever a tick occurs, you're going to need to check which beat we're on. If we're on the first beat of the bar, then you need the frequency to be 2000, otherwise the frequency should be 1000. Think for a moment about what that might look like as a state machine diagram. We have 4 states, we have transitions in a particular order between the states, and we have particular conditions for transitioning between the states. It might look something like this. If our metronome is fixed to 120 beats per minute, then every half a second we're going to move from one state to the next state, and our output is going to be a tick sound involving the exponential envelope. The frequency of the tick will depend on which state we're entering into at that particular moment. Pause the video here and see if you can make this example work. Okay, here is the result. This is a very simple example. There's no controls for this metronome, just a regular ticking at 120 beats per minute. You can see here the variables involved in calculating an exponential envelope that we would have looked at in the previous lecture, and we can see here a constant defined, k metronome beats per bar is equal to 4. This is just me giving a name to a number so that later on in my code it's very easy to see what the code is doing, and it's easy at the top of the file potentially to change the number of beats in the bar. We have the counter, which we're using to count audio samples to decide when the next tick should be. That follows the ideas given in lecture 9. The interval is the amount we need to count up to before we start the next beat, and we can see that that is calculated here inside the setup function because we need the audio sample rate to be able to know what it should be. Finally, we have this variable called g metronome beat. This is effectively our state variable. It tells us which of the beats of the bar we're in at any given moment. Its valid values are going to be 0, 1, 2, and 3. And each time a new tick occurs, what we want to do is increment the value of the beat. When we get to the end of the bar, we should reset back to the beginning, and depending on which beat we're in, we're going to choose the frequency differently. Let's go down to setup and see how that works. As usual, we have a for loop counting through the number of audio frames. Inside of there, we have this counter, which we saw in lecture 9. We're incrementing g metronome counter, and we're checking if it's greater than or equal to the interval. If that's the case, a few different things happen. First of all, we reset the counter to 0 so that we can count up again for the next beat. Second, we reset the amplitude to 1.0 to start a new exponential envelope. Then what we do is we increment the state variable. We say g metronome beat plus plus, go on to the next beat. If the beat has reached the end of the bar, in this case, if g metronome beat is greater than or equal to 4, then we reset back to the beginning. And when we are resetting back to the first beat of the bar, we set the frequency to 2000 Hz. In every other beat, the frequency is equal to 1000 Hz. Therefore, when we calculate our oscillator and we multiply it by the envelope here, we're going to have tick sounds at one of two different pitches depending on which beat we're on at the moment. The rest of this code is quite standard. We write the audio to both of the output channels. We can run this and hear what it sounds like. And we can hear very clearly that every fourth tick is at a higher frequency. Let's extend these ideas a little bit. This step will require a breadboard with a button and an LED. The first thing to do is to add some LED feedback that blinks on each of the metronome beats. We covered this already in lecture 9, so I won't talk more about it here. But the thing that's new in this example is to add a fifth state representing the metronome being stopped. What we want to do is use the button to start and stop the metronome. When the button is clicked, if the metronome was in the off state, it should start clicking from the beginning of the bar. But if the metronome is in any of the other states, then clicking the button should move it to the off state. You may therefore want to define a special value for the off state, which could not be a valid beat number, for example, -1. Here's the circuit to wire up on your breadboard. The LED is connected to digital pin 0, and the button is connected to digital pin 1. Of course, if you want, you can also add a potentiometer to this example like we did in lecture 9 to change the metronome speed. Pause the video here and see if you can make it so that you can press the button to start and stop the metronome. Okay, here's our expanded code using a button and an LED and an extra state. You can see the first thing we do is we define this special value k metronome state off, and we set that to a value of -1. This is the special value of state corresponding to the metronome being off as opposed to being in one of the 4 beats. We have otherwise the same variables as before, although we're beginning the metronome in the off state, so we need to click the button to start it. I've also had to add some variables to deal with the button and the LED. I provide names for the numbers of the pins so that they're easier to work with later on in the code without forgetting what we're dealing with. And then I also need a variable to keep track of how long the LED should be on. The details of this are in lecture 9. Finally, to detect button presses, we need to always save the previous value of the button as well as the current one so that we can detect edges as they come in. Inside of setup, we have a few things to calculate beyond what we had before. We have to calculate the LED interval. I've made each LED blink to be 50 milliseconds long, and we have to initialize the GPIO pins. Particularly, the LED has to be set to an output because all the pins default to be inputs. Inside of render, we have some extra code as well. We are using digital read to read the current value of the button. Now, this is our code to detect whether the button was just clicked. We've seen this before. The button was just clicked when its current value is 0 and when its previous value was non-zero. And the reason that the pressed button has a value of 0 is that the button is wired between the input and ground, rather than between the input and the power supply. If we detect a button press, we need to decide what to do with it based on the state. We'll say here, if the metronome was previously in the off state, then we're going to start it in state 0, i.e. the first beat of the bar. We're going to reset the counter to 0 so that we start counting from the beginning of the beat, and we're going to reset the envelope to 1.0. We set it to a frequency of 2000, which is the higher pitched tone for the beginning of the bar. Otherwise, if we click the button and the metronome was not previously off, now it should be off, and so we set the metronome beat state variable to kmetronome state off. Then finally, this line of code stores the current value of the button into the previous value so that this if statement works properly the next time around the loop. Now, if the metronome is not off, then we need to do a few things here. Notice that I've added an extra if statement around the code that we had before, so that we're only incrementing the counter when the metronome is not in the off state. If the metronome is in the off state, then none of this will happen. However, we still will generate output because we're still going to have the sine oscillator running and we're still going to have the amplitude scaler. The way this particular code works is that we're always having the exponential envelope decay even when the metronome is off. The important part here is that we have to have some value of out when the metronome is off. If we forget to calculate anything at all and we forget to call audio right when the metronome is off, we might end up with some unexpected behavior. Lastly then, we have the code to turn the LED on when the current counter is less than the LED interval. Notice that I've also added a guard here where I only light up the LED if the metronome is not in the off state. This exclamation point equal, of course, this means not equal to, and the double ampersand is the logical AND condition. So both of these things need to be true in order for the LED to light up. Now, here we can have a look at our circuit. We have the button and the LED on the breadboard, and now we can run our code and see how it works. Our metronome starts out in the off state, so we can click the button to turn it on. And now we can click it again to turn it back off. Now, you might have heard something slightly funny there. There was a sort of double click, and if I press this button a few times, you'll hear more strange business. Notice that last time that I pressed the button and it was off, and it stayed off, it didn't turn on as expected. What's going on here? Is this a bug in our code? It's actually not a bug in our code, it's a bug in the button, so to speak. The button has spring-loaded metal contacts, and as we've seen before, they quite literally bounce, so that every button press involves not one event, but several. So we sort of get a randomizer in terms of whether the metronome ends up in the on or off state every time we press the button. The good news is that the state machine is actually the perfect tool to deal with this problem. We're going to undertake a process known as debouncing, which is a way of compensating for the bouncing spring-loaded contacts. There are several different approaches to debouncing, from very simple ones and even electrical ones, for example putting a capacitor across the button terminals, to more sophisticated ones involving various forms of timers. Now, before we get into any of that, what I want you to do is run the example called scope button from the companion materials. You'll need a button hooked up to digital pin 1 on this example. The example is complete, you just need to run it, and once you do that, you should open the Bela oscilloscope. Once you open the Bela oscilloscope, there are a few controls to set so that we can really clearly see what happens when we press the button. You can see these in the upper right-hand corner here. You should set the trigger mode from auto to normal. You should set the trigger direction to be negative, and you should set the trigger level to be something slightly greater than 0. When you do this, you should be able to see what happens to our digital input signal when you press the button. Pause here and try it. Okay, here you can see the scope button example. It's quite simple. I'm just counting through the number of digital frames in the block, reading the button pin and logging it to the scope. I'm also writing the value to a digital output pin for an LED. Because our button is wired up where pressing it results in a 0 value, I'm writing the inverted value of the input to the LED so that the LED will light up when I press the button rather than when I release it. So I can run this example and I can open up the scope. Now remember that we need to start by adjusting the scope controls, which we'll do here. So I'm going to change this from auto mode to normal. I'm going to change it from positive to negative trigger. I'm going to turn the level up a little bit. And then I'm also going to turn the scale of this channel down a little so we can see it more easily. Now what's going to happen here, I can close the controls, is that when I press this button, we can see what happens. And you can see that we don't oftentimes get a clean edge. Sometimes we can get quite messy transitions on press and, in fact, on release. That's push, that's a release, that's a push, that's a release, that's a push, that's a release. My personal experience is that sometimes these larger size breadboard buttons are particularly bad in terms of being bouncy compared to the small ones. Depending on what kind of switch you have, you may find the bouncing is better or worse. But what I want to learn from this example is essentially how long does the bouncing typically last with a decent button push. So if I push this here, that was pretty clean. I release that, you can see on the horizontal scale that that bouncing lasts just a couple milliseconds. Press it again, release, press a few times. Oh, you can see here that bouncing lasted maybe upwards of about 10 milliseconds. And just depending on the button push, we might get different lengths of bouncing. We're going to use that information to design our debouncer, because what we're going to do is we're going to set a timer that waits a certain amount of time once it sees one of these edges before it concludes that there are any further button presses. Now, as I said a minute ago, debouncing works very well as an application of a state machine. What we need is actually not 2 states, but 4. We need 1 state for the button not being pressed, we call that open. We need a state for the button being pressed, which we call closed. And then we need 2 additional states, which I'm going to call just closed and just opened. These are transient states that we enter when we first see an edge on the button, and we linger there for only a certain period of time before we move on to the next state. The question that we had was how long we wanted to wait in those states, and that's what we use the oscilloscope for. In my particular example, I'm going to use 50 milliseconds, because pressing a button more than 20 times per second is not so easy anyway. The following question is, how do we wait for that amount of time in one of these states? The answer to that is that we need to remember when it is that we entered the particular state, or have a counter that we reset to a value of 0, and then we can count samples as we usually do. This brings us to the next task. Using the example called debounce, implement this state machine that implements debouncing. What you need is to have the 2 states, just closed and just opened, completely ignore the input value of the button, and instead just count up a timer until 50 milliseconds have elapsed. The other thing to do to check if this is working is when you transition from the open state to the just closed state, toggle the value of an LED. What that means is that one button push should turn the LED from off to on, and the next button push should toggle the LED from on to off. Notice that pressing the button is what generates the transition from the open state to the just closed state. Nothing particularly special should happen when you release the button. As before, you might find it helpful to look at what's going on the oscilloscope. Pause the video here and try it. Alright, this is my completed debounce example. To begin with, I have declared the 4 states in the diagram: open, just closed, closed, and just open. These are just 4 unique numbers, and we're going to use the names instead of the numbers later on in our code. I need a state variable, which is just a simple int that tells us which state we're in at this given moment. We're going to start out in the open state, meaning that the button is not pushed. We have a counter and an interval that we're going to use to implement the delay in the just closed and just open statements. This works very similarly to what we did in the metronome. And then I need 1 further variable which tells us whether the LED is on or off at this given moment. Notice that in this case, the state machine is only for keeping track of what the button is doing. I'm not trying to fold in LED on and LED off into one compound state machine where we have different states for clicking the button when the LED is on and clicking the button when the LED is off. This is just a matter of taste and style in any particular application. We have our usual setup code where the LED is set to an output, the button to an input, we initialize the scope as before, and we have to calculate the debounce interval to be 50 milliseconds. Inside of render then, we have our digital read statement, logging that to the scope just like we did before. The real state machine code starts here, and you should recognize this structure from what we talked about a few minutes ago. We have a series of if statements, which is checking which state we're in. So, for example, if we're in the open state, do one set of things. Else if we're in the just closed state, do a different set of things. Else if we're in the closed state, do a third set of things. Else if we're in the just open state, do a fourth set of things. So this block if, else if, else if, else if is a very important structure. Inside of each of these if statements, we then find further if statements. This is looking at the inputs to our state machine. Specifically, our inputs are the value of the button and the timers that we have in certain states. So if we're in the open state, we know from the diagram that we are looking for the button to be closed. A closed switch has a value of 0 in this particular wiring, so if the value is equal to 0, then what we're going to do is we're going to change state. We're going to have a transition from the open state into the just closed state. This also implies resetting the counter to 0, because we're going to use this counter inside the just closed state to measure how much time has gone by. Finally, as we said in the specification, when the button is just now clicked, which is this very transition, we want to toggle the value of the LED. The way we're going to do that is to invert the variable gled state, and we'll see down at the bottom of this code that we write this value to the LED. We can look at the other states next. Inside of the just closed state, the point is that we are not interested whether the switch is open or closed at this immediate moment. We expect the switch is going to be bouncing during this particular time, so all we're doing is marking time. We're incrementing this counter and we're checking if it exceeds this interval. Once the interval elapses, then the only thing we need to do to transition to a new state is to store a new value inside of our state variable. So in this case, we move to the closed state. What that means, of course, is that the next time around the for loop, we will enter this block of code instead. If we're in the closed state, then what we're looking for is the switch opening. That means that the value is not equal to 0, and the very first time that happens in this state, we're going to transition to the just open state. Again, the just open state relies on a counter or a timer to measure the amount of elapsed time, so we need to reset that counter to 0 when we make the transition so that it has a reliable value inside of this block. The just open state is the mirror of the just closed state. We're not actually reading the value of the button at all in here because we expect it to be bouncing. Instead, we're just incrementing the counter and we're checking whether it exceeds the interval. Once it exceeds the interval, then we set the state back to the open state. Notice I don't do anything else here. For example, I don't toggle the LED here because I only want the button press and not the button release to cause a meaningful action to take place. Then the only last thing I have to do is to write the LED state to the digital output. So this is another example of a system where I can't externally observe which state the button is in at any given time. All I can do is see the results of the state machine, which is that the LED might be on or might be off, and it's toggled based on pressing it. So let's run this code and we'll look at it. So here's our button LED setup as we had before. When I press the button, the LED turns on. Press it again, turns off, on, off, on, off. There we go. So this is much better than what we had before. State machines are useful for all sorts of different things, and one other comparatively simple example that can benefit from a state machine is a comparator. Now, nominally, a comparator is a very simple analog component. It's basically something that outputs high or low, depending on which of two analog inputs is bigger than the other. Usually the way we use these in practice is to have one of the inputs be a fixed threshold and the other one be a variable input which represents the signal that we're interested in. So we have a situation where we have a continuous input and a discrete output, only high or low. From a programming perspective, there's a very common statement that does basically exactly this. And what kind of statement might that be? It is, of course, the if statement. We can say, if our value is greater than some threshold, then we do one thing, otherwise we do a different thing. Now, there's a problem we'll sometimes have when we work with real analog signals, and this is true whether our comparator is implemented as an electronic component or an if statement. The problem that we might have is noise. Our signal might have on top of it a lot of random variation, such that as the signal approaches the value of the threshold, we might find it crossing above and below the threshold repeatedly in a short period of time. This can result in a very messy output not dissimilar to the bouncing button. What we need is a way of telling whether our signal is above or below a threshold, but rejecting the small amount of noise on top of it. How might we do this? The term that we use in engineering for this is hysteresis. What hysteresis means is that our system has a different behavior in the upward and downward direction. In this particular case, we're going to adjust the threshold that we're comparing to, depending on whether we're looking for a low to high transition or a high to low transition. A comparator with hysteresis is known as a Schmidt trigger. The idea is that it provides noise immunity by insisting that our signal go across a higher threshold before it goes from the low state to the high state. Then, to get from the high state to the low state, the signal value has to traverse this gap to get below a lower threshold. The implementation of a comparator with hysteresis is essentially a state machine. It involves two states. There is the high state and the low state, and the transition conditions are going to be different for each of the two states. This is what I want to implement next. First of all, hook up a force-sensing resistor to analog input 0. Remember that in addition to the FSR, you need a fixed 10K resistor so that you form a voltage divider between the FSR and the resistor, which goes into the analog input. What you should find is that if you don't implement the hysteresis, when you press the FSR slowly, that you end up with a whole stream of different messages going from high to low, low to high, and back again. But your task is to implement the hysteresis. What this means is that when your system is in the low state, you should look for the signal to cross a threshold of 0.75. That means that the FSR is almost completely pressed. When the signal crosses this value, then you can move from the low state to the high state. Then to get back from the high state to the low state, you need the FSR to cross a value of 0.25. What that means is that a slow press of the FSR or a slow release should never result in a rapid toggling on and off, because you essentially need a complete press and release cycle to move from one state to the next. In addition to using the LED to indicate the output state, you might find it helpful to print a message to the console whenever a state change takes place. Inside of the Bela render function, we never use the printf statement. The reason for that is that it's not real-time safe and it will cause a mode switch. Instead, we use this special function called rt_printf, which has the same syntax as printf, but is safe for use in render. So build this circuit, wire up this code, and see if you can make it work so that pressing the FSR and releasing it always produces a clean on and off on the LED. Pause the video here. Okay, here is the hysteresis comparator code. We have here the declarations for the LED pin and the pin with the analog input. Notice that they're both called pin 0. This is because this is digital pin 0 and this input is on analog pin 0. I've also declared two states for the state machine. There's a low state and a high state. The comparator is going to start in the low state. Now, just for purpose of illustration, I've started with both thresholds equal to 0.5. So in this case, it's as if there's no hysteresis at all and it's just a simple comparator. We'll see what that looks like in a second. Inside of setup, we have a simple check to make sure that the digital frames and the analog frames are the amount that we expect them to be. We are setting the LED pin to be an output, and we're initializing the scope with 2 channels. Inside of the render function, notice that I'm counting digital frames because I'm not actually using audio in this case. Actually, the digital sample rate and the audio sample rate should be the same, so if you count audio frames, you should end up with the same result. We're reading the analog pin. Notice we're reading frame n/2 because the analog sample rate is half of the digital or audio sample rate. And then the output is either going to be high or low depending on the state of the comparator. Here we have our state machine code. We are asking if the comparator state is low, then we're going to compare the reading to the high threshold. What that means is that normally we're going to look for it to exceed a certain higher threshold before we switch into the high state. If the reading does exceed the higher threshold, then we can print this message here to say we're going to the high state, and we change the state to be G comparator state high. Alternatively, if we're in the high state to begin with, then our output should be equal to 1 so that the LED is turned on, and we're going to check, is our reading below the lower threshold? If our reading is below the lower threshold, we're going to print a message and we're going to switch the state to be in the low state. Finally, we write the value to the LED, and we log both our raw reading and the comparator output to the oscilloscope. So we can run this and we can see how it works. Okay, and we can open the Bela oscilloscope. Now again, in this first example, I'm not using any hysteresis. Both the high and the low comparator thresholds are equal to 0.5. So you can see the blue line is at 0 right now because the FSR is less than 0.5. And when we go above that, you can see that the blue line goes up to 1.0. And then back down. Now it might be easier if I change the controls so that we can actually see the blue line when it's at 1. So here we go then. You can see if we push on the FSR, it goes up to 1.0, then back to 0. Now look what happens when I go back and forth around 0.5. You can see I have all this glitchy business. This is the effect of the noise, which is causing the value to oscillate up and down rapidly between 1 and 0. And this is not desirable behavior. This is what we're trying to get rid of with hysteresis. So we can stop this now. So now let's change the thresholds to be what the example asked for. So the high threshold will be 0.75 and the low threshold 0.25. And we'll rebuild this project to see how this looks. Now look what happens when I press the FSR. We're still in the low state. The blue line is still sitting at the 0 level. But when I push it enough, it switches over and the output is equal to 1. Now it's going to remain in the high state, and look, I can move this up and down and the value doesn't go back down to 0, because we have to have the value of the FSR drop below 0.25 before we return to the low state. So you can see as I go up and I go down, we never have this noisy middle region anymore. So this system is much more noise robust than the previous version, which is exactly what we want. And that's all for today. We've now laid the groundwork for the next lecture where we're going to see the ADSR, or Attack Decay Sustain Release envelope. This is a fundamental building block of many synths. For those of you following along as these videos are coming out, the frequency of video posting may slow down for the next couple months while I take a bit of a break. However, we still have many more lectures to go, starting with the ADSR envelope, moving on to MIDI, and then to a number of interesting topics in block-based processing of audio signals and high-performance processing on embedded hardware. So if you haven't already, be sure to click subscribe so you stay tuned for the latest updates. Over the next couple months, we also intend to post a number of guest videos by members of the Bela community, so be sure to check those out when they come out. Thanks for following along, and see you soon!